All right, welcome back to pre-calculus here. So today we're going to talk about the graphs of sine and cosine. And let me just go through what that is first, because the homework is really good, but it kind of starts in the middle. So let me go ahead and share my screen with us here. And let's start looking at some graphs, okay? So what I'm going to do is I'm going to kind of make a t-table for each of these. Okay, so we're going to go ahead and draw this. Don't worry, we're not going to stick with just this. All right, so here we go. We have x and we have our y. All right, so we're going to have 0, pi over 6, pi over 4, pi over 3, and pi over 2. All right, and then for sine, right, y is equal to sine x. Okay, we're going to have sine of 0, okay, which is 0, the sine of pi over 6, which is a half, sine of pi over 4, right, which was 1, which is square root of 2 over square root of 2. Okay, the sine of pi over 3 is square root of 3 over 2. Okay, and then pi over 2 is equal to 1. Okay, now these were problems that we were supposed to kind of memorize. I'm going to go ahead and pause so I can go get my calculator here, but we're gonna keep going with some decimals so we can do some graphing. Okay. All right. So all I'm going to do is I'm just going to put some x values and y values in here so we can actually use this as a graph. So what does pi over 6 look like? Right, pi over 6. I mean, it's 30 degrees, right? But what's the actual value here? Okay, so this was approximately, so these are going to be the approximate values. This was 0.52. Excuse me. Oh, no. How about we start with 0 like we did on the other side? Okay, so we have 0, 0.52. Okay, we have pi over 4. Okay, so the second function pi is divided by 4. Okay, 0.79. Okay, we have pi over 3. Okay, 1.04, 1.05. Okay, and then pi over 2, which is 1.57, I believe. All right, because that one never comes up. I don't have it memorized. 1.57. Okay. And on the other side, right, we have a 0. Okay, we have 0.5. We have 0.7071. We have 0.866. And we have 1. Okay. So if I was going to make a graph here, right, we could do this. We could look at our first quadrant, okay? But I'm going to keep going with this until we have a couple more problems, a couple more values here. Okay, we're going to go into the second quadrant. All right. So here's my x, here's my y equals sine x. Okay, and do the same thing. Here's pi over 2, right? And then look at what's happening. Okay, so we've gone here, okay, and now we're going to come back down around. This is the unit circle. Okay, so we're going to be coming back down around here. Okay, pretend this is round. What sine value is doing is it's measuring these the vertical distances as we go around. Okay, that's what we're doing. Notice there's a big change in vertical difference for small linear distance at the beginning of the circle, but not so much vertical distance as it was at the beginning. So when we get close to the top, right, there's less vertical distance that we're changing versus the x values that we're changing. Okay, our graph is going to reflect that. So we're here, we're at pi over 2. We're going to go a little bit further. Okay, so this is going to be 2 pi over 3. Okay, so we're going to have 2 pi over 3. Okay, that's going to be 3 pi over 4. Okay, and then we're going to have 5 pi over 6. Okay, Like I said, I'm just chasing the regular angles around the unit circle with this. Okay, we're not, I picked these numbers specifically because we're supposed to know them. Okay, and we could do from there. So our sine of pi over 2, right? We said that was going to be sine of pi over 2. That's equal to 1. Okay, and then sine of 2 pi over 3. Okay, what's the reference angle for 2 pi over 3? Here's 2 pi over 3, right? It's 2 pi over 3. Reference angle, right? This guy here, this is 1 pi over 3. We have to go 1 pi over 3 more in order to get to the horizontal. Okay, what was the sine of pi over 3? Right, this was the square root of 3 over 2. Okay, what's the reference angle for 3 pi over 4? Okay, that's here. Okay, how much further do we have to go to get to the horizontal? 1 pi over 4, right? So 3 pi over 4 plus 1 pi over 4 will give us 4 pi over 4. That'll be the horizontal. So that is square root of 2 over 2. Okay, and then we have 5 pi over 6. What's my reference angle? How much more do we have to go to get to the horizontal? We have 5 pi over 6. How much more do we need to go? It's 1 pi over 6. Okay, so this is sine of 5 pi over 6, which is the same as sine of 1 pi over 6, which was half. Okay, and remember, we are measuring the vertical distance. We have the sine of pi, right? That's this line here. What's my vertical distance on this line? 0. Okay. And again, we go through and do an approximation of, I'm going to erase, I'm sorry. I'm going to do an approximation of the decimals for these numbers so we can kind of get an idea, excuse me, of scale. Okay. Don't worry, we will draw a much better picture. Actually, we won't. A computer program will draw a much better and more accurate picture. Okay, but if it comes out of a human hand first, like it'll be a little bit more accessible. Okay. All right. So just to kind of go through and say, well, what was pi over 2? Pi over 2 was, so this is decimal wise. All right, this was 1.57. My y value was 1. 2 pi over 3, I don't know. So this is, oops, this is 2/3 times pi. Okay, this is 2.09. Okay, square root of 3 over 2 is still 0.866. Right? Okay, so 0.866. Okay, 3 pi over 4, I don't know. 2 point something, but here's, so 3/4 times pi. Times, oh, how would we do times pi? There we go. 2.35, sounds good. Okay. And then we have 5 over 6, right? 5 pi over 6. So we're going to go with 5 divided by 6 equals times pi equals, and we got 2.61. Okay, and then we get to 3.14. Okay, so we type these in. So this is 0.7071. Okay, 2.61, that's going to be 0.5. And then 3.14, that's pi, so that's going to be 0. Okay, the only reason I'm doing this, so when it says exact, okay, these numbers are exact. Okay, over here, these are the numbers that are exact. Over here, these are approximations, because you know what we're going to do? We're going to graph. All right. So let's see, what do we have to do with x values? We have to go from like 1 to, or 0 to 3. Okay, so why don't we call this one 1? We'll call this one 2. We'll call this one 3. I'm going to try to make this about the same distance up and down because I'm trying to be pretty accurate with my axes so that you get a sense of scale. And again, we're going to show what's going to happen here in a minute, and then we're going to take a human approach to it. Okay, So my first thing, 0, 0. Second one, 0.5, 0.5. Okay. So here's about 0.5. Here's about 0.5-ish. So we'll call that our first point. This is pi of, or this is sine of pi over 6. Okay. Next one, we have 0.79 to 0.77. Okay. It still kind of looks like a line, doesn't it? I mean, we're up like 0.7 to 0.7. Okay. And then we're going to have 1.05 to 8.66. So 1.05 to about 8.66. Okay. And then 1.57. So here's 1.5 up to 1 here. Okay. So what we want to do is we're going to go ahead and draw something like this. Right. All right. And I'm out because I don't think that actually quite made it. Okay, but that's all right. So 2.09, we're back up here at, right, here's our 8.866 here. Okay. Okay, 2.35. Okay. We're back down here. Okay. And 2.61 down here. And then at 3.14, we're down here at 0. Okay. Now I know it looks a little bit like a semicircle, but the equation for a semicircle is y is equal to the square root 1 minus x squared. Like, why do I know that? Because x squared plus y squared equals 1. What was this graph? Right? This was a circle. All right. So let me get it, and then the other side, right, is going to flip. Okay, we're going to be on the negative sides because as we're going around the circle, what's my horizontal distance in the third and fourth quadrant? They're the same as the first and second quadrant, but they're all negative. Okay. Now, can I go around the circle more than once? Absolutely. So this is going to go up and keep going around. This is going to go down, and it's going to snake forever and ever in both directions. Okay. So if I want to take a longer thing here, we can go. We're going to have a graph that looks kind of like this, but better. So let me go ahead and show you what's going on here in Desmos. Okay, and then we can kind of get an idea of like what's going on here. Okay, so we're going to say y is equal to, we're going to say x is, no, we're going to say y is equal to sine x. All right, so let me go ahead and phase in a little bit here with me so I can give a projection mode rather than this is what we have. Okay, so this is what our sine looks like. It keeps going, because we can go around the circle in a positive or negative way an infinite number of times. So it just keeps going and going and going and going and going. Okay. So let me just show you what's going to happen if I say, well, this is y is equal to square root of 1 minus x squared. Okay. So this is a semicircle. Okay. So you can see, even if I wanted to do something of a 1 minus this thing, okay, it's just not quite the right graph, okay, for what's going on here. Okay. Could I move it over? How do I move something? How do we move something to the right? Okay, so instead of this equals, could I do something like 1 minus? I want to move this 2 off to the side here. Could I do something like minus pi over 2? And why don't we do a plus here so we can change that? Okay. I didn't want to move this all the way over, but I did want to move it over a little bit. Oh, minus 1. Okay. There we go. Okay. So I'm trying to line up my semicircle with this part. Okay. And it back in here to make it. I will not. I'm trying to get this thing to kind of look a little bit like a circle for us. Not doing very well. Okay. But it's not like a wagon wheel. Okay, it's not doing that for us. Okay, it's not doing that for us. Okay, -1. Not quite. Okay, but this little curve here bends in the wrong way. It's way too big for what's going on here. Okay, give me a moment. All right, so it's not a semicircle. It's not just a one wheel going around here. Okay, it's a little bit different. Okay, because look at here. By the time it gets to 1, right, we are at pi/2. So it's kind of like a squished wagon wheel. Okay, but that's also why it keeps going on and on and on. Okay, so all we're doing is we're just measuring the vertical distance. Okay. All right. To do a cosine, okay, cosine is measuring the horizontal distance. Okay, so why does it start from 1? Okay, it starts from 1 because when I've got my circle here, I've got what's the horizontal distance that I start off with? Right, the horizontal distance I start off with is 1. And then when we get to pi/2, what's my horizontal distance here? It's 0. Okay. And then we have -1 over there. Okay. That's a better picture anyway. Okay, and then we come back down around. So these are negative horizontal distances. Okay. When we get to the bottom here, we have a 0 horizontal distance because it's straight down. And we come back to 1. Okay. So that's why we have a U-shaped type of a piece here. Okay, so it starts and ends at 1 horizontal distance away from 0 to 2 pi. Okay, at pi it's negative, but it is kind of, again, it's not a wagon wheel. It's kind of a stretched out and squished a little bit wagon wheel. But all it's doing is measuring horizontal distance. Okay, so that's what we're looking at for the graphs of sine and cosine. All right. Let me go back to this for just a moment. When we showed you this, right? This is our theta. This is our sine theta. This is our cosine theta. Okay. So remember, we talked to people about this one. We said this is 0, pi/6, pi/4, pi/3, and pi/2. And remember the mnemonic to get this thing. Okay, square root of 0/2, square root of 1/2, square root of 2/2, square root of 3/2, square root of 4/2. And this one went backwards, right? This went square root of 4/2, square root of 3/2, square root of 2/2, square root of 1/2, square root of none/2. Let me go ahead and do this for a second. Dot you out for a moment. Okay, so look at how cosine starts, right? It starts up tall and then falls. Okay, and then sine, right, starts from 0 and rises. So I had a hard time, even the mnemonic. Okay, I had a hard time committing this to memory. I was like, well, which one starts at 0? Which one starts at cosine? And because I memorized the I remember what the graph looks like, it's easy for me to pick this out. It's like, oh, that's right. Sine starts from 0 and climbs. Cosine starts from 1 and falls. Okay, because I do have to think about what this graph looks like in my head first before which one of these columns actually I like for which one. Okay. When you get to calculus, you're gonna find like there's a negative sign in front of the slope of the cosine. Okay, and if you remember what the graph of cosine looks like, okay, does it make sense? It starts off with, right? It starts off with a negative slope because it starts up at 1 and then falls down to 0. So this is a negative slope here, right? If y is equal to 1 minus x, okay, we're getting a similar type of a thing here. Okay, let's go with 5. Okay. Okay, so we're getting a falling piece. Okay, so that's what you're supposed to remember for this. All right. So let's, that's the basics of how to graph a sine and a cosine. Okay. So if you remember, like, okay, if I remember what the graphs look like, the values are going to follow from that. Or it's okay if you like the values first and then want to construct the graph from the values. That's normal. You can do it that way. All right. So they're both different ways to think about it. They're both perfectly fine. If you find another way that you like, then feel free to use that. Okay, it's okay. Just because I showed you one way doesn't mean you have to keep that way. All right. So let's start going through some homework with us, and that way we can kind of see what's happening. Okay. Now the book only makes you graph one wavelength. Okay, that's all we do. Okay, so for the first one, they just want us to pick it out. Like, okay, cosine looks something like this. We're set. We're good. We're done. Let's move on. All right. You know what I have to do? Let's check that and go. Okay. The other thing is that all of the little, the little graph transformations you guys learned in college algebra, it is exactly the same thing. Okay. And they want to do for like all the little vertical stretch, vertical shift, horizontal shift, vertical shift, or horizontal compression or stretch. They're all going to be the same things. Okay, and we're going to go over them as we meet them in our little homework so we can see what's happening. Okay, so answer the following questions: for y equals cosine x, express your answer in simplified fraction, express points as ordered pairs. All right, now the domain. Okay, let me go back to our picture here. What does the domain of cosine look like? Okay, now I'm taking a little bit of a risk with this because the domain of cosine technically is it can go in every direction. Like, was there a rule that says you can only go around once on the circle, right? Or am I allowed to go around twice, or 3 times, or 4 times? Do I have to go around in a positive way? Can I go around in a negative way? Sure. We used to spin records backwards all the time. By the way, they don't mean, or there's no messages. Okay. I know you want to hear them, but it's not, it's like, how do you divorce your human intuition or your human expectation from what's real? Okay. So I know it sounds like some stuff sometimes, but I don't think there's anything there. Okay. But yeah, you could play the record forwards or backwards, and you can do it an infinite number of times. It doesn't matter. So my domain for cosine here, that's infinite. Okay, that's from positive infinity to negative infinity. All right, so domain interval, we'll put that in there. Okay, and we'll put in a negative infinity there and a positive infinity there. Okay, we'll check. Really, we're getting hung up on that, huh? Okay. Okay, the range. Again, we'll look at our graph. What's the tallest number we get? What's the highest number? What's the lowest number? Are there anything that's smaller or larger than -1 to +1? No, that's it. That's as best as you're going to get. Okay, -1 to +1. So if anybody tells you, I'm like, here's a problem for you. Like, cosine of theta is equal to 7/6. You're like, well, immediately, that's a lie, because the ratio that we get here has to be between -1 and +1, right? There is nothing above that. There's nothing below that. So you have to remember, like, oh, -1 to +1. All right, so we'll go here. Actually, we'll go, because it can include -1 and +1. So let's hit this one. -1, +1. Okay, by the way, the same thing is true for the sine in both of these. Domain and range for sine is also, domain is negative infinity to positive infinity, interval range -1 to +1. The amplitude, let's meet amplitude. Now, y is equal to a cosine theta. The absolute value of A for amplitude, okay, that's what that means. So it's just the absolute value of whatever number happens to be out front. In algebra, we call this a vertical stretch, okay? In trig, we're going to call it amplitude, okay? They mean and do exactly the same thing. They have the same jobs, all right? So let's go ahead and take a look at what I'm going to do is I'm going to put an A here, A cosine, and it's going to ask me to put a slider in here, okay? So what happens if I'm moving my A bigger and bigger and bigger, right? We get a vertical stretch. And if I change it to negative, right, it's going to, first off, -1, right? Instead of starting up here, it's going to start down below, and it's going to be the opposite way, okay? But notice what's happening. Like, it's still a vertical stretch, okay? So it doesn't really matter if it's positive or negative. We don't care. We're just telling you what's the biggest and smallest number we're going to meet here, okay? That's all we're doing here. So amplitude, absolute value, okay? Positive, just take the positive one and write down the number that's before it. Okay, so that's all we're going to do there. So on a vanilla sine or a cosine, amplitude is 1. Okay. 7 more points. Okay. Period. All right. Period for sine and cosine and secant and cosecant. Period is 2 pi. It's the length, it's one wavelength. It's the length of one waveform. When we get to tangent and cotangent, they're a little different, okay? They only have a period of pi, okay? So it's half the size, okay? So sine and cosine both have a period of 2 pi. When we get to do a problem with that, I'll show you a simpler way of doing this. All you have to remember that on a basic vanilla sine or a cosine, that we start at 2 pi and we end at 2 pi. We start at 0, and we get through one waveform at 2 pi. Okay, so we know the period is 2 pi on this one. Okay, 2 pi. Oh, they want this pi, right? Cosine symmetric is symmetric too. Okay, so notice that the cosine, I get to show you guys this. This is so awesome. Okay, symmetric to the y-axis, right? The same thing happens on the right side as happens on the left side. Okay, this is an even function. Okay, so we're going to have even function. Remember, this is f of x is equal to f of x, right? What that's saying is if we have negative x's, negative numbers, it's going to do the same thing as going to be on the right. Okay, vice versa, right? So it's an even function. It's symmetric to y-axis, just like x squared, right? This is symmetric to the y-axis. So the same thing on the left as the right. We can fold it over, and we're going to be okay. All right. So let me show you this. This is so cool. Okay, if I do say so myself, all right. So let's look at cosine. Now let's look at something that's close to cosine. Okay, this is what you're going to learn in calculus, second semester. So y equals, we're going to start with 1. Okay, and because that's where cosine starts, is 1. So we're going to say minus x squared over 2. Okay, and what we're trying to do is we're trying to approximate the cosine with this polynomial. Okay, and around 0, it's actually a pretty good match, right? If I only needed to get like between, these two, values between, like, say 0 and maybe 1/4, like I got a pretty good match here. Okay, maybe even down to 1/2. Okay, we've got a pretty good match. What if I add in, I say x to the 4th over 24. Okay, check it out. That's even closer. Okay. And then I'll spill the beans on you. We'll say x to the 6th over, I'm going to say 6 factorial. Okay. Let me go ahead and put this one as a dotted line. We'll keep this one there. Okay. So the more and more and more of these terms I add, the closer we can get to actually getting to a cosine. Okay. I don't like that. I like that one a little bit more. Okay. I mean, but it's only good up to a certain point. Okay. It's only going to be good up to a certain point. The more of these terms you're going to have, the more accurate it's going to be. Okay. So you can decide, well, when you're trying to solve equations, it's going to be up to you to decide, like, how far do I want to carry this out? Okay. Now, cosine or factorial, like we had 4 factorial here. This is 4 times 3 times 2 times 1. Okay. 0 factorial, we define that to be 1. What factorial is doing is saying how many ways are there to arrange something, right? So if I've got 4 distinct pieces of candy, how many different ways are there to arrange my 4 pieces of candy, right? And I've got 4 choices for the first spot. Once I put a thing in here, I've got 3 choices, I've got 2 choices, I've got 1 choice. For 0 factorial, it's like, I don't have any candy. How many ways are there to arrange 0? And instead of saying none, we just found it to be more convenient to actually define this thing to be 1 instead. So how many ways are there to arrange 0 pieces? Like 1. I got an empty table here. Okay, enjoy. So that's how we define factorial. Okay, it stops at 0. Okay, when you count 2, there'll be a better formula for it. But until then, you're stuck with this. Okay. It's not a bad thing. Most people are at this level. Okay. So that is, notice with the exponents here, they're all even. Cosine is an even function. Okay. So we'll come back and we'll look at that. Oops, I want this one. Function is around the y-axis. Oh, by the way, tangent, okay, tangent is, or not tangent, sine, tangent too, but sine, okay, is an odd function. Okay, because it looks something like this. Okay, like it actually goes down, this comes back up, okay? So tangent is an odd function. I'm sorry, I keep saying tangent. Sine is an odd function, okay? Because what happens in the first quadrant happens in the third quadrant. So the idea that f of negative x looks like negative f of x, all we're saying is that when we go over to quadrant 2 and 4, that the y values are the opposite, the negative of what we had in the x values. We are not distributing the negative sign out. We're just saying it's a property of symmetry. Okay, so we're not factoring it out. You can't do that to a sign. It's a symmetry. That's why that's happening. Right? And just to let you know about sine, so get this, put this back in. We have y is equal to, we have x, okay, minus x cubed over 3 factorial over 3 factorial, okay, plus x to the 5th over 5 factorial. Okay, and do you see how this is getting closer and closer and closer to approximating sine? Okay, all of these numbers here are going to look like odd. Well, they're not going to look like, they are odd. They are odd exponents, every one of them. Okay, 1, 3, 5, 7. Sine is an odd function. Okay, so that's what we use to approximate these things. So if we need to say, well, we only need to be this good. Okay, again, once we get to about up here, right? it's not so good. I had to go out 4 terms for this. Okay. So certainly we're a bit more off when we get out here. Okay, these two are a bit different. Okay, so that's what we use when we want to approximate. Okay, so let's see here. The intercepts for these points, right? Where was it? 0, and it was 0. Remember, what is cosine? Cosine is measuring the vertical distance. I'm sorry, the horizontal distance. Where was there no horizontal distance? Here and here. Okay, so my cosine, right? Okay, my cosine had 0 horizontal distance when we were at pi over 2 and at 3 pi over 2. Okay, we're going to do this one problem, and then I'm going to stop and take a break. I'll put another video up instead. Okay, so we are at pi over 2 and 3 pi over 2. Okay, those are my x-intercepts. Oh, sorry. There is only one x-intercept, and it's the first one. Okay, it's a 1. Okay, so let's go back and look at that. No, that's y-intercept. On the interval x-intercepts, this is where we are cosine. Yeah, that should be all right. Am I misreading this thing? Right, because we talk about lines, right? Lines equal y because I'm x plus b. B was my y-intercept, so that's where this happens, right? So x-intercept should be where this happens. Okay, and this was at, yeah, this is pi over 2 and 3 pi over 2. What are we doing here? All right, did I get the right formula? I did. I know. Oh, I should have, okay. Oh, points. I didn't read the instructions. Express points as ordered pairs. Okay, so that's my fault. Okay, but pi over 2 and 3 pi over 2, that's where we are. Okay. On the interval 0 to pi over 2, what are the maximum minimum points? Not going to fool me again. Okay, x was 0, y is 1, x is 0, I'm sorry, x is 2 pi, and y is 1. And the minimum point, that's where, right, that's where this one is. It's not 0, it's -1 is more minimum, right? And this was at pi. Okay, so we're going to have our parentheses, we're going to have pi, comma 0, -1. Okay. All right, so that's what they want for that. Okay, so I'm going to stop us here. Okay, and we will continue what's going on with the rest of them, and I think I'll have a chance to show you some of the other ways of graphing this, not other ways, but other techniques of graphing it. Okay, so I'll stop us here, and we'll continue this in a moment. Okay.